Good afternoon. Welcome back to ECE 207. Today we are getting into new material. The previous material is for homeworks 1 and 2, and that will be the material covered on exam number 1. And that material, as far as topics and what you can and can't bring into that exam, very quickly, it's closed notes and closed book, but I will allow you one sheet, 8.5 inches by 11 inches of notes, and that can be front and back. Bring a calculator and something to write with. That's about it. And then the topics, there is a practice exam. Do you think it would be at all helpful if I were to maybe work through the old exam in like a tablet and post that online? So I would have the audio. I'll see if I can do that sometime this weekend or before. So we'll see about getting a somewhat of a review for exam number 1 posted to the D2L site. Today what I want to do is talk about Chapter 3. This is new material. It will not be on exam number 1, but it will be on subsequent exams. Please don't tune out immediately because it's not going to be on the first exam. It will be on the second exam. Chapter 3 talks about new devices, new elements. These resistors give us a fair amount of element and design possibilities, but they don't give us that much. We want to be able to do more than just instantaneous change of voltage or current levels. The inductors and capacitors that we'll be talking about in Chapter 3 allow us to store energy. Ideally, they store it and then they give it back. They store it and give it back. And we need to learn how to model that or include that in our equations that govern our dynamics in the circuits that we'll be dealing with. Today what I want to talk about are the functional characteristics of the capacitor and the equations that govern that. How do we combine capacitors in parallel and series, and then we'll try to get into inductors. Oh, you thought I was asking. Oh, you already know. So capacitors combine just the opposite of resistors, so to speak, and inductors combine like resistors. Okay, now we can all go home. We've covered half of today's material. Let's try to see why that is the case. But before we do that, let's just look functionally at how these capacitors operate, or functional operation of a capacitor. Here is a schematic diagram. There's the rest of the network, and these two horizontal lines actually represent the parallel plates of a capacitor, and there is not a physical connection between those plates. There could be something between those plates in the form of what's called a dielectric. It could just be an air gap, but it could be some other material. Here are the plates. And obviously the one below it. The idea behind this is you actually, we would like to be talking about current and voltage relationship on this capacitor, and how are those currents and voltages related. We need to now try to understand that. If we start looking at this, you will find that, and sometimes it's easier to just think about positive charges. If we were to dump a lot of positive charge on this plate, the top plate, there is no physical connection, electrical connection between the top plate and the bottom plate, those positive charges will start to accumulate, but they're going to push the positive charges on the lower plate away and effectively create negative charges there, which are actually the electrons. But now that we have this separation of charge, that now leads to an electric field, E, between these plates. And the buildup and the release or the contraction of that electric field is where the energy is stored on this capacitor, and that's actually how you store energy and then release it. Store it and release it out into the rest of the circuit, is by this accumulation of charge. Let's say that's Q. And then the release of that charge or the depletion of that electric field, the shrinking or collapsing of that electric field. So the electric field builds up and collapses, builds up and collapses, and that allows us to establish this relationship between what we can think of as current flowing with that capacitor and this current voltage relationship. We actually have a charge voltage relationship that we can think of based on this diagram. And in particular, the charge, Q of t, is proportional to the capacitor voltage, which I guess I should have labeled here. This electric field is volts per distance, volts per meter. There's obviously a distance between those plates, and that distance then, when you take that into account together with the electric field, allows us to establish a voltage drop or a voltage difference across those plates. The charge and voltage are proportionally related to each other, and that proportionality constant is C, or capacitance. This is then this parameter or proportionality constant that now we can play with or use similarly to how we've played with Rs or resistors. Now we have a relationship between charge and voltage on this new device, this new element that's charging up with energy and then releasing that energy back into the circuit. And it's doing that through this electric field. What are the units on that capacitor? There's a lot of different combinations of units, aren't there? If we look just at the equation, charge has units of coulombs, and now we have this C, and voltage, let's just say that we have volts. Now we need to multiply something by volts to get coulombs. So that seems to be the obvious units, but you can also think of coulombs in a different way. So now the units are actually coulombs per volt, or if you thought of current, current is charge per second going through some particular area, and we could then think of coulombs as actually amps seconds. If we multiply coulombs per second times seconds, that will give us coulombs. And another way of thinking of a capacitor in terms of its units would be to say, oh, it's amp seconds per volt. Well, that gets a little ornery to keep saying amp seconds per volt, so we just define that to be farads. And 1 farad is really big. We normally play with units that are in the 10 to the minus 6, 10 to the minus 12 farads. Microfarads, picofarads, femtofarads. 1 farad is a huge quantity. So if you see something that looks like a farad, although now they are making capacitors because we want to start using things that are basically capacitors like batteries. Now we are getting small devices that can have big units on the farads in terms of their units. Now, if we go back and look at this relationship, charge and voltage, and they're proportional by the capacitance, or C. Q is equal to CV. Current isn't there explicitly, is it? We do not have an I. But I is just coulombs per second. Well, there's a Q, there's coulombs. If we would differentiate that, if the charge was changing as a function of time, then if we looked at that time rate of change of our charge, that would give us our current. Or if we simply differentiate that relationship, Q is equal to CV, we could maybe introduce our current, and then we would have a current voltage relationship for the capacitor. If we do that, then we can see that we have I of t, which is dq of t dt by definition of what I of t, our current, actually is. Now if we say, well, that's actually the derivative of the right-hand side also. We can't do one thing to one side of the equation and nothing to the other. We have to be consistent. That now, as long as this proportionality constant is constant, if it's not changing, then we can pull it out or factor it out of the derivative sign. So if, and in some cases we actually don't have a constant C. In some microphones, there may be capacitive microphones, and the sound wave pushes and compresses those plates closer together. You can electrically measure that or sense that, and then your C is time varying. But let's just assume that we have a set of plates that are fixed, and C is now constant. If C does not change, then we can establish our current voltage relationship of a capacitor, which I always tell the ECE students they need to remember this relationship until they retire, and that's I is equal to C dV dt. Just like V is equal to IR. That's our current voltage relationship of a resistor. Now we have determined a current voltage relationship of a capacitor. And if you want, you can now draw this picture that's similar or consistent with the resistor picture that we've used before. The current voltage capacitor relationship is I sub C of t is equal to C dV sub C of t dt. Or we now have, in terms of pictorially, we have this capacitor C in our circuit. That current voltage relationship means that we would have a positive current flowing from left to right. And again, this is now not, well, it's a displacement current. There's not any current actually going across that gap, but the change in current causes the causes the charge to vary, and effectively you have current flowing through that circuit. But now that goes into this positive side of the capacitor. That passive sign convention is consistent then with the current voltage relationship I is equal to C dV dt. Question?
Real quick, why the current flows without the connecting wires?
So why does the current flow without the connecting wires? What we're doing is you have to go back to that first picture that we drew and say, okay, if charge is going on one plate, then you could sort of think of a membrane if you wanted to get a different view of it, and maybe you have fluid on one side of the membrane and it smashes that membrane. That membrane sort of smashes everything down below it. And that's effectively what's happening with the charge. The charge goes and builds up and goes away, builds up. If the positive charge is up top, negative charge is down below. Then if you fill the top with negative charge, you have positive charge down below. And that movement across the gap establishes this displacement current. So it's physically not flowing, but this time rate of change of charge allows this current to effectively be moving around in your circuit. Even though electrons are not flowing across that gap, they're being displaced. You now have this displacement current. If some are going, if the positive charge is going, let's say that left plate is getting a lot of positive charge, what does that do? Well, that attracts a lot of negative charge, but that effectively is saying, oh, positive charge is going away. So do you see how it sort of jumps? I would jump, but I would fall down. This floor is slick. Plus, they wouldn't see it anyway. I'm just being recorded. Do you kind of see how that happens then? So you sort of run into it, and the fact that you're running into it says, whoa, to the other side, and it just keeps going. All right, no more questions like that, right? You can only take so much of that in one lecture. Where were we? Let's now, one way to maybe remember this relationship, has anybody ever heard of Eli the Iceman? Wow, okay. So now you've heard something new. Eli the Iceman. Maybe you are going to have trouble remembering that I is equal to C dV dt. Just remember Eli the Iceman. Eli is related to our inductor. Ice is related to the capacitor. And what you have to remember, I is like I. L is my inductor, proportionality constant, L. C is the capacitor, but E is the old school version of voltage, electromotive force, instead of V. So that would be hard. It would be Eli the Iceman, or I don't know, Ice. So it's Eli the Iceman, okay? So this is like V. This is voltage.
It can be so confusing with electric field, though.
Oh, don't even think about the electric field, I guess. Because really what we're doing, we're dealing with currents and voltages. The electric field is sort of hidden or buried underneath this voltage. We aren't going to really have to go deep into it and learn or understand or deal with the electric field. Okay, so we'll be dealing with the voltage. But in this case, what I'm saying is ice is now I sub C, that's our current, is equal to this constant C, and then I differentiate the next variable, which is the voltage, E. So that's dV sub C dt. That's ice, and what we will subsequently develop is the current voltage relationship of an inductor, which is V sub L, or E, and now we use the same structure. On the right-hand side of the equality sign is L, di sub L of T dt. So there's Eli and ice, Eli the Iceman. And then now you can hopefully remember, oh, it's V is equal to L di dt. That's the inductor current voltage relationship. And for it, you have the same type of structure. Here's L, here's V sub L of T, and which way do you think the current's flowing? With the passive sign convention. It's going from left to right. Here's I sub L of T. There will be our inductor relationship. But before we get there, let's spend a little bit more time with I's, or I is equal to C dV dt. This is Eli, and ice we just talked about. What are some observations about this ice? Did anybody bring ice with them today? Oh, no food and drink allowed. Thank you for obeying the signs. But the next time you get a cup of ice, what are you going to think about? Eli, thank you. And this current voltage relationship. You're going to be sipping your drink, your cold drink, and you're going to go, I'm studying my ECE 207. Oh. So you can start deriving the relationships on the napkin and impressing your friends or roommates or whatever, right? Okay. What are some observations? When might we find I sub C, our current through the capacitor, being 0? Based on this differential relationship, which is why you're doing your differential equations class right before this one, apparently, is so that you'll understand how to do this analysis. If I now say that I sub C of T is 0, what's that telling me about my voltage? When would dV dt be 0? When V sub C is a constant, right? If V sub C is constant, that derivative is 0, and so we have 0 current flowing in our capacitor. If we have a constant current, if constant voltage across that capacitor, the current is going to be 0. I sub C of T, or our capacitor current, is 0 when the capacitor voltage, V sub C of T, is constant. That's one observation, and you can get that just by looking at the current voltage relationship of a capacitor. What else can you observe? Well, if you look at that equation, you can also convince yourself that, wait a minute, V can't change instantaneously, and then, because I would have garbage on the left-hand side. If I tried to differentiate something that was changing instantaneously, it just doesn't make sense. Meaning the voltage across a capacitor cannot change instantaneously. In our capacitor circuits, we would then expect that voltage to not be changing instantaneously on the capacitor. If we are dealing with an ideal capacitor, which is really what we are going to be working with here in this class, these ideal capacitors can only store energy. Well, maybe I should say store and release energy. It does not absorb or dissipate energy. We will probably, the question was, are we going to assume all of our capacitors are ideal? We will, unless stated otherwise explicitly in the problem. If there is some leakage, or if there is some parasitic behavior, we'll try to identify that explicitly. If we do not, then we're assuming that that capacitor is storing and dissipating energy, and that's all it's doing. There's no sort of resistance associated with that. Although in a practical capacitor, you may have some parasitic resistance associated with it. Where is our energy stored in this capacitor? What's it stored in? A little bottle? In the electric field. So this energy is stored in a field, and that field is an electric field, which is caused by this separation of charge. And that creates this voltage. And that's what we want. We want to worry about this current voltage relationship of a capacitor. Before we go any further, let's just talk about the power associated with the capacitor. Now that you're in DiffyQ, you know how to play with all these differential relationships. But what's the power, instantaneous power formula that you've already learned that you can probably use with these new elements that we're defining, which this first one is a capacitor? What product of terms create power? I squared R, well, that's IV or VI, right? Voltage times current. Voltage times current is still valid for creating power or for defining power, but it has to be associated with that particular element. In this case, it's the capacitor voltage times the capacitor current. Again, with that picture that we've already sketched that shows us how the current is going into the positive terminal of the voltage on that capacitor. What are the units on that power? Watts. That hasn't changed. But now we can create some more interesting expressions for that power formula. If we now plug in the current voltage relationship for current, we could say, oh, this is V sub C of t, and what was ice? Or I was created from this ice, which is C dV sub C of t dt. But what is C times V? Wasn't that just charge? And now we know that the charge on that capacitor times the time rate of change of the voltage across that capacitor will give us the power in that capacitor. Those are some useful formulas. But it may be more interesting to talk about the energy stored in a capacitor. And we know how are energy and power related. What do we have to do with power to get energy? Integrate. Energy is the integral of power. If we now say, well, what's the energy of this capacitor? We could say, well, that's the integral from 0 to t of P sub C of tau d tau. Which, if we use some of these relationships for power that we just derived, here's this integral from 0 to t, and now let's use this C, V sub C of tau, dV sub C of tau, d tau. That's a power formula times d tau. Now we can cancel some of those differentials. And we're now left with this integral. And if we're assuming C is constant, it can slide down if we want, but I think you can see that we now have C, V sub C of tau, dV sub C of tau. And maybe we could probably say something like, now that we're integrating with respect to V, maybe we should change this to V sub C of 0, and this is now V sub C of t. We're going to integrate from the beginning value of our capacitor voltage up through the final value of our capacitor voltage. And that's going to give us what happens when we do integral of x dx. What's the integral of x dx? 1/2 x squared, right? So now we're basically doing that with voltage, and we now have 1/2 c v sub c of tau squared evaluated at, let's say, v sub c of 0, or when tau is equal to 0, and v sub c of tau equal to t. If we assume there was no charge initially on that capacitor at time 0, whatever we define time 0 to be, then we could see that the energy stored in that capacitor after t units of time from time 0 would just be 1/2 c v sub c squared. I'm assuming that v sub c of 0 was 0. So we had no charge on that capacitor, and so we had no voltage initially. And there's one formula that you might see quite often, is that we have the energy of our capacitor is now 1/2 c v sub c squared of t. And that has units of joules. And now that we know all of these different relationships for voltage or voltage on a capacitor, we could use some of those and say, oh, our energy of the capacitor we could rewrite. Q is C times V, so we could pull a V out of that V sub C squared, and we now have 1/2 Q of T, V sub C of T. And that's another expression for the energy of that capacitor. Or we could do it again and say V, Q is CV, so V is Q over, how do I want to say this? V is Q over C, so that we now have that's equal to 1/2 Q squared of T over C. And again, that's in joules. Using this formula, Q is equal to CV. And solving for V, or getting rid of V in that left portion of the expression of the energy of our capacitor. Questions on that? Question?
How can we substitute tau for t? It seems as if we're going to equate them anyway. If we could just leave it as t.
So now, why did we substitute T for tau?
Is that the charge time constant?
What? No, tau is just our variable of integration. So why did we pick tau or substitute tau for T? You could use whatever you want. I just used tau. Tau is not a time constant. Tau is just a variable of integration in this formula. And we needed, you usually don't use your limits on your integral as a variable underneath or inside your integral. So I was just trying to be different or unique, saying, oh, I want to integrate something, and that something I'm integrating is a function of a variable. I'm just calling that variable tau. It's just notation. I could have called it sigma if that makes it easier. So it could have been P sub C of sigma, d sigma. And I'm integrating this function, P sub c of sigma, where really sigma is time, but I'm evaluating that from 0 to t. Let's now talk about how we can combine capacitors. And show why they are sort of just the opposite of what we're used to thinking in terms of combining resistors, and why that's true. Let's just convince ourselves of that. Let's look first at the case where we might have some capacitors in parallel. We have 3 capacitors, just for illustration purposes. What do we know about those 3 capacitors' voltage? And C1, C2, and C3 are not equal. They're different. They're different capacitors. So they have different sizes. What do we know from this picture? What do we know about the voltage across C1, C2? Are they related? Those 3 capacitors are in parallel, and they then share this common voltage V. What do we know about the current flowing, the displacement current on C sub 1? But we'll just draw it as if it was a current flowing. What do we know about I sub 1? What do we know about I sub 2? And what do we know about I sub 3? We know that I1, I2, and I3 have to satisfy ICE, don't they? I is equal to C dV dt. But in that I is equal to C dV dt, I's are different, C's are different, the V's the same. But we also know that these 3 I's are related to I sub S. In preparation for exam 1, what's the relationship that exists between I sub S and those 3 I's? Is there a K or a last name that begins with K that might? Kirchhoff, right? We have KCL that we can rely on. We know from Kirchhoff's current law that I sub S, the current coming in, that's all just one node that I've dashed or indicated with the dashed red circle. That's I1 plus I sub 2 plus I sub 3. And now we can write down our ICE relationship in terms of the capacitor C sub 1 and this voltage V across it. How can we rewrite I sub 1? Is that true? That's just C dV dt. What about I sub 2? I sub 3. That dV dt is the same. For all 3, we can factor it out. And now we have C1 plus C sub 2 plus C sub 3 times dV dt. Or we could say, you know what? Why don't we just say, instead of those 3 individual capacitors, why don't we say there's just one equivalent capacitor relating I sub S and that voltage? If we did that, then we would say, oh, I sub S is just this C equivalent times dV dt. What's that tell us about our parallel capacitors? If we have a bunch of capacitors in parallel, we can simply add their capacitances together and create one equivalent capacitor, or these parallel capacitors add. That's not what happened to resistors, was it? We can't just add resistors that are in parallel. That's the difference. What kind of resistors could we add, or what configuration on our resistors are required so that we can add them? Series. Let's look at what happens when we have capacitors in series. For capacitors in series, let's just have this loop with the top capacitor being C sub 1, the vertical capacitor C sub 2, and the bottom horizontal capacitor C sub 3. We will have a current flowing in that circuit. We can call it I. And we could label these voltages so that they obey this passive sign convention that we've established, and now we can immediately write down this ICE relationship for all three capacitors once we get there. To get there, though, we want to show a relationship between all of those voltages, and that can be obtained by saying, oh, KVL has to be true around this particular circuit. KVL in this case is minus V sub S plus V sub C sub 1 plus V sub C sub 2 plus V sub C sub 3. That's equal to 0. And what do we know about each of those? Or, yes, we know the current is the same. Maybe we should go a little bit aside and look at the voltage relationship on these capacitors. So maybe right now we do this and we say, let's just do some background. We know that I sub C of t from ICE is C dV sub C of t dt. And we can do some of our algebra that we've now learned in our calculus and differential equation classes. We can say, oh, this differential in voltage is now C, or I should say 1 over C, times I sub C of t dt. And now I can integrate with respect to time on both sides. I can say, oh, let's just go from t naught to t sub 1 dv sub c, and what do you think I'm going to use inside my argument for v sub c? It's a dummy variable. It's a variable of integration. It really doesn't matter. I was going to use tau, but I don't know that you like that. So now it's going to be sigma. That's just a variable of integration. This is now equal to 1 over c, and 1 over c is a constant, this integral from t naught to t1 of I sub c, and this could actually be something else, couldn't it? It could be an alpha, d alpha. It could be sigma. It's a variable of integration. What do we now know? Now the left-hand side is just the voltage on our capacitor at time t1 minus the voltage on that capacitor at time t0. And that's equal to this integral of our current, where current is what? Coulombs per second. So if we integrate that, we're just going to end up with charge. But let's just keep it in the integral form. We're going to be integrating from T0 to T1 of I sub c of alpha d alpha. Or we know that the eventual voltage on that capacitor is the initial voltage on that capacitor plus this integral relationship of current. And if we start with no charge on that capacitor, this particular piece would not be there. It would go away, and we would have V is equal to 1 over C integral of I for this current voltage relationship of a capacitor. That is our aside, meaning now we can use this information in this KVL equation. Meaning, we now can replace all of those V's with this 1 over C, but now the 1 over C's are going to be unique to the particular C that we're interested in, but the current's the same because we're talking about this series current. So that now we can say, oh, V sub S, our source voltage, is actually equal to 1 over C1 integral from, let's just go from time 0 up to time t, I of sigma d sigma plus, and that this piece is V sub C1 of t. The next piece is 1 over C sub 2 integral from 0 to t, I of sigma d sigma plus 1 over C sub 3 integral from 0 to t, I of sigma d sigma. This is our V sub C2. There's our V sub C3. And all of those integral pieces are the same. We can factor that out or collect all of our capacitor pieces. And realize that, oh, that looks like just an equivalent capacitor times the integral of our current through that capacitor. Our capacitors initially were in series. Which now says, oh, if we want our equivalent capacitor when they're in series, 1 over the equivalent capacitor is equal to the sum of the reciprocals of all of our capacitors. Or the equivalent capacitor is now 1 over C1 plus 1 over C2 plus 1 over C3 in this particular case. Questions on that? How about we do a little class participation? I need to wake you up. What do I want you to do? I want you to find an equivalent capacitance between these two nodes, A and B. And it's not going to be just that one capacitor, C1, so don't hand in your paper just yet. It's now going to be this. What is the equivalent capacitance looking into terminals A and B? That's your class participation. Question. In terms of C1, C2, C3, C4, and C5. This is, so now when you go home you can replace all those C's with R's and say what's my equivalent resistor to study for exam number 1. But for exam number 2 you can do this problem. So you should be able to do it now based on what we've talked about so far. Yes? You don't have to simplify anything. You can just leave it in some combination of C's. C1, C2, C3, and if you get some complicated rational expression, that's okay. Are we finished now that I've given you that? Well, at least you're awake. Let's take one more minute and finish up. Pass those to your right if you're in the two right sections, and in the left section, pass those to your left, if that makes any sense. I think that's what we've been doing most of the semester, isn't it? And let's try not to take 10 minutes passing those to our right. I'm going to assume you are finished. Pass those to your right, or you know if you're passing to the left. How do we attack this problem?
Pass towards the center.
Pass towards the center, wherever the center is. I'm not going to walk up the center. That would be too fun. And probably I would break something of mine or the hardware, the furniture. How do we attack this problem? Just like you're going to attack it on Tuesday if it was resistors? Yes? No? How will you work this? Are you seeing the series resist? Which way do we work? Do we work from right to left or left to right?
Right to left.
Now everybody's leaving now that we've done the class participation for the day, huh? If we work from, we need to work from the furthest away from those terminals, A, B, which is to the right, and go to the left, and start collapsing from the right as we work to the left. If we do that, here is maybe the first piece that we want to try to collapse. Those are in series. And how do series capacitors combine? Those are the easy ones, right? No. Those are the ones that are opposite to the resistors. Let me call that a C3. Oh, you guys don't like bars. Oh, well, depends on the bar. If it's over a variable, you don't like the bar. Is that right? You like a bar if it's in a restaurant? I'm sorry. Oh, you're not, I'm sorry, you're not of age. So, here we are. I'm sorry. C sub 3, it won't let me go now. It's forcing me to a bar. There. That's a hat, a funny hat. C sub 3 hat is, because of this series combination, this is making it ugly in a hurry. 1 over C sub 3 hat is equal to 1 over C3 plus 1 over C4. Is that correct? Or I could have said C sub 3 hat is now this C sub 3, C sub 4 over C sub 3 plus C sub 4. Similarly to how resistors combine in parallel. I'm going to avoid the ugliness, and so I'm just going to call that mess C sub 3 hat. And if I need it, I'll just plug in those numbers. What's my next strategy? Now I have C sub 3 hat in parallel with C sub 5. Does everybody see that? I now have this picture in part of my circuit. I have C5, and that's now connected to C sub 3 hat. And those, because they share 2 points in common on the two ends, these are in parallel. And what do I want to call that? Let me call that C sub 5 hat, that combination, which will now be C sub 5 plus C sub 3 hat. That now ends up being, in my original circuit, I had C1, C2, and now I've combined all of those on the right into this C sub 5 hat. Are those in series, all three? No, because of this connection right there and that connection, meaning C sub 1 is not in series with all of the other two capacitors. Here's A and here's B. I can only go so far as to combine those two. Those two are now in series. C sub 2 is in series with C sub 5 hat, so that now my C sub 2 hat is going to be C sub 2 times C sub 5 hat over C sub 2 plus C sub 5 hat. Once I've done that, then I end up with my C1 and C sub 2 in parallel, which allows me to say that the final equivalent capacitor that I was trying to find is now this parallel combination of C1 and C sub 2 hat. Did your answer look this clean?
No.
Because you carried through all of those different combinations, which is fine. But now I tried to do it in a form or a strategy that would help you see what was going on. And we didn't try to complicate things by carrying along all of that extra baggage, which were all the formulas or the expressions. Questions on capacitors? That's ICE. Let's now talk about Eli. Let's now get into inductors. There is going to be what I will call my coil form, or what you might hear somebody refer to as the core of your inductor. If you were in elementary school, did you make an electromagnet out of nails and wire and a battery? That's what? You did that in class just yesterday. That's fine. But now that wire is behind that form, and it's going to come around, and then it's going to go back behind again, And so now we're making all of these we're wrapping a coil around this coil form. And so this is now what I will call the coil. We've now built or created an inductor where the inductor has a current, I sub L of t, and it has a voltage drop across that coil of wire, and that voltage drop is V sub L of t, the inductor voltage. If we now apply a time-varying current to that configuration, where we have this wire wrapped around a coil, or a coil form, a time-varying current creates a time-varying magnetic flux, or you could think of this as now a magnetic field. And that magnetic flux is going to link the coil, or those elements of the coil, so that now all that wire is getting linked together to create this inductor. So linking the coil, which induces a voltage across those coil windings.
What does it mean to link the coil?
You have one piece of that coil. So what does it mean to link the coil? You now, instead of just having one wrap around that coil form, you have several windings. So now essentially what you have is you have this field that's combining together. So one is helping the other. So they're linked together. So I'm not building something with physical links. I'm coupling these with a field, or this magnetic field. So now I have this induced voltage that I'm calling V sub L of t, and that induced voltage is proportional to the changing current. And that proportionality constant is the inductance, which in equation form, that says that this induced voltage, V sub L of t, is proportional to this time rate of change of current in that coil of wire, di sub L dt. And there's Eli. V is equal to L di dt. And we want to keep track of that. And like we did for the capacitor, we can also talk about the units on this inductance. And here we have volts equaling something times amps per per second. And inside the L, here are the units on L. We now need the result to give us volts. And we need to get rid of the amps, and we need to get rid of the seconds. So now this is volt seconds per amp. And that gets a little ornery to keep track of. So we've just defined that to be henries. And you probably anticipated that name. That looks like a Henry, a volt second per amp. There's your Henry. So Eli has units of Henry, or L. L is a Henry. And this ideal inductor, just like we had the ideal capacitor, the ideal inductor, that's only going to store energy, can only store and release energy. It's not going to absorb energy like our resistors do. Those are resistances, and those are where we have our heat loss in our circuit, or this energy loss. But these inductors and capacitors just store and release, store and release. It cannot absorb energy. That's the ideal inductor. In this case, our energy is not stored in an electric field, it's in a magnetic field. So now we have our energy is stored in the magnetic field, which is surrounding the coil. So this magnetic field expands and contracts, and that stores and releases this energy to allow us to create circuits with more interesting characteristics than just instantaneous change in current and voltage, which is all we get with resistors. Now we're going to be able to store and release this information, or this current voltage relationship. Let's make some observations before I release you.
What's the variable for magnetic field?
So now we have flux for our magnetic, we have these flux linkages, and then we have our magnetic field. It's similar to what we had with our electric field. We're not going to worry about labeling the magnetic field. We're just worried about this inductor, whose energy is stored in this magnetic field, and so we're building it up and releasing it, building it up and releasing it. What we want to worry about is this current voltage relationship on the inductor, which is V is equal to L di dt. Just like a resistor, except now it's a differential relationship, similarly to how we did our capacitor. What are some observations that we can make? What do we know about the inductor voltage? V is equal to L di dt. If we had a constant current flowing, what do we know about Eli? What does Eli tell us about the voltage? V is equal to L di dt. If we differentiate a constant, then we know that the voltage is going to be 0. And so now if we have constant current flowing in this inductor, that inductor looks like just a wire. There's no voltage drop across it. It looks like a straight wire. Also, we know that this inductor, or an inductor, yes, I should just leave it. I'm just getting frustrated, so I'm just going back and forth. And I think we're going to have to pick up at this point on A week from today. Tuesday when we see you again, be ready for the exam.